Okay, welcome to today's video everyone. Find all complex numbers z satisfying the equation e to the 2z minus 2 times e to the z plus 2 is equal to 0. Okay, so you should notice that this is a quadratic equation in terms of e to the power z. So we can write this as e to the power z squared minus 2 times e to the z plus 2 is equal to 0. And now we can apply the quadratic formula to solve for e to the z. So we have e to the z is equal to minus b, which is going to be 2, plus or minus the square root of minus 2 squared minus 4 times 1 times 2 all over 2. Okay, we can simplify this. This is going to be 4 minus 8, which is minus 4. And so we have the square root of minus 4, which is 2i, divided by 2. And so we have that e to the z is equal to 1 plus or minus I. Okay, so we're going to have two separate equations now. E to the z equals 1 plus I, and we have e to the z equals 1 minus I. Okay, now, if z is a complex number, as it says in the question, therefore z is equal to x plus iy. And so we can say that e to the x plus iy equals 1 plus I. And the same thing here, e to the x plus iy is equal to 1 minus I. Okay, now we can split this exponential up by using our indice laws. So this becomes e to the x times e to the iy. And let's change this now to modulus argument form. So the modulus is going to be the square root of 1 squared plus 1 squared, which is root 2. And the argument of this number, this complex number, well, the argument is going to be tan inverse of the imaginary part over the real part, which is going to be pi on 4. So we're going to have cis pi on 4. We can do the same thing here, and we're going to get root 2 cis, and here, because we're going to be in the fourth quadrant, this is going to be minus pi over 4. Okay, now we can apply Euler's theorem, or Euler's formula, to e to the iy, and this becomes cis y and the same thing here, equals root 2 cis minus pi over 4. Okay, and now we can equate our moduli and our arguments. So we're going to get e to the x equals root 2 and y equals pi over 4, but we can add integer multiples of 2k pi, and the same thing here, e to the x equals root 2. Might just put a line to distinguish the two. E to the x equals root 2, and y equals minus pi on 4. But again, we can add integer multiples of 2 pi, because we're just going back around and getting back to the same complex number. Okay, now let's solve this for x. So if we take the log of both sides, the natural log, ln of root 2, now this is ln of 2 to the power of half. So ln of 2 to the half, which is 1/2. We can use our log laws, bring this down, so it's a half of ln 2. And so our solution for z here, z is going to be a half ln 2 plus I times the y value, which is pi over 4, plus 2k pi. Okay, and here we can do a similar thing. We can follow this same process and get that x is equal to a half log 2. And so we can say that z is equal to 1/2 ln 2 plus I times the imaginary part, or I times y, so minus pi on 4 plus 2k pi. And if we really wanted to, we can combine these two and say that the solutions for z are this set. The set which is a half log 2 plus, now you can see that we can combine these two into 2k pi, and really the only way we combine them is by putting plus or minus pi over 4, such that k is an integer. Don't know if you could say that bit there, but k is an integer. Okay, and so these are the solutions of z for this equation here. Thanks for watching.